So, the $64 question is, do you want any of these gone over? By the way, Shamila, I need you to make up a quiz real soon, okay? Are there any of these that you want me to go over? No? Not going to fess up to it. All right, well.
Have you looked any further at the one we did yesterday?
Yes, I have. And I can certainly talk about that. I'm just not sure how much of that you're going to want to hear. All right, well, I'll start on that, and you guys have a little think about. Sam, have you looked at them? Have you got the list somewhere where you could look at it? Give him that and have. Sam, come here. Look over these and see which of them, if any, would be harder for you. Because, I mean, basically, if I give you a list of problems, even if some of them are kind of hard, and say, do these, prepare them, I do feel entitled to put them on the darn quiz. So, okay, the thing we were looking at yesterday gave us some discrete time signals. Yes, that's true. It gave us some discrete time signals, and it said what would the spectrum look like with different sampling times. So, broadly speaking, the sort of thing they gave us was x of n equals an expression, and then they said ts equals, and there were ts's of 2 or a half, typically. Now, what I said yesterday was I wasn't really sure what they wanted me to do with the spectrum. I wasn't sure whether that spectrum was to be radians per second or radians per period. And I went and looked in the book, and it showed a picture like this. So you can, and I've basically recorded something on this and posted it in case I didn't get to it. What I concluded is that all that they're really doing in this question, okay, I'm not sure anybody's paying attention to me with the possible exception of Jake, and Luke is kind of looking. Yes, I know you're looking at me, Luke. People whose names end in KE are paying attention, everybody else is asleep. What they did is they the book drew a spectrum, said, suppose this is your x of omega of your original discrete time signal. They said, and then they said, we're going to define a quantity y of n that equals x of qn. Now let's think for a second about what that means. Q is a positive integer. So q might be 3 or something, right? Obviously q doesn't equal 3. Q is positive integer. But if it does equal 3, what that means is y of 0 is x of 0, but y of 1 is x of 3. I got kind of waylaid while I was doing my little recording thinking, what does this mean? Y of 2 is x of 6, etc., etc., etc. Sarvash, right? Were you here yesterday? I was going to talk to you about cricket. Okay, so basically all you are doing, and I think this is what we said yesterday, all you're doing, if you're sampling with a bigger sample time, assuming it's an integer multiple of the old sample time, all you're doing is just sampling every qth sample. So we're not confused about what that does, and I think what I said at the time was essentially, your spectrum is going to. What they did is they said if this is minus W to W, the spectrum of Y is minus WQ to WQ. And that answers my question, because my question was, what do they mean by the frequency? You know what I'm talking about, Jake? What does that tell you that they mean by the frequency? What is omega? Is it radians per second or radians per sample time?
Per sample time.
It is, isn't it? Right. And I just didn't know which one it was. And I think that what's going on here is that they're just thinking in terms of a data file, where the entries in the data file are, you know, indexed by an integer. And if you just got a data file with sounds in it or something, and there's an integer labeling things, you really don't care in some sense what that integer is. You're just processing it as frequency per sample time, and that's what they seem to be doing. And I just wasn't sure, because when they're talking about continuous time signals, then it's all radians per second, but in discrete time, they seem to be squarely in a world of radians per sample time. So, okay, it's kind of obvious, I think, that if you change from this x of n to this y of n, you're sampling less often, so frequencies seem higher. So you're still operating in a range minus pi to pi, but the meaning of pi has changed, if you see what I mean. Okay? So, and of course, there are copies at minus pi and pi. So there'll be another one here and another one here. So you'll have, your overall signal might look like that, for example, if WQ is getting up close to, and this point here is minus pi by 2 and pi by 2. So if the sample time is doubled, then it's pretty easy. And I think that's consistent with what I said yesterday, Sam, right? Okay, so that's the question we were discussing. Now, this is where, if you've got any questions relevant to the quiz, you should leap in and ask them, because what I'm going to do now is interesting to me, but it's probably not going to come up on the quiz. So take your pick. Okay, so if the sample time they're asking you to use is smaller, then the question arises, what do you do? Because if they give you x of n, but they tell you TS is a half, then you don't know the values in between, right? And it seems to me there are two choices that have how to interpret the question, and I couldn't actually find anything in the chapter that said this is what we mean. I think Sharmila said that she thought what you should do for the intermediate, you know, if TS is a half, you know what happens every second beat, but on the intermediate beats, you just don't know the value, strictly speaking. You could set it to 0, is what I think she expected you to do. Well, we could, I mean, okay, so suppose that what you do, because I think it's it's one of the logical possibilities, is you say x of n is whatever it is, but then, I've still got a pen, no. Suppose we have some old signal, but every second beat is a 0. And we know these values are some simple signal, but there's zeros in between. What do we expect the spectrum of that to be? How would you tackle that?
Wouldn't the spectrum be the same?
I don't think so. I mean, there's a couple of ways you could think about it, right? I mean, one thing that I could do I don't know how you want to do this. You might say that you've got a product of your original function with some function that goes 1, 0, 1, 0. I mean, what if I say that I've got a function that is this? What's that period going to be? I've got to figure... Stop it. Suppose I've got a function that's 1, 0, 1, 0, 1. maybe I can say that I take my original x of n, somehow modify it so that it's defined at the half integer moments, and then say that the actual function is a product of the original function and this baby. I mean, okay, Shamila, what was the first, or you've got it. Do you have it in front of you, Sam, this question? He's put it away. Quite. You're looking at it. Are there any that you're interested that you need to go over? That's the hard one. Okay, well, we'll come back to it in a minute. Now, work with me on this because I don't exactly know what I'm doing here, so don't just sit there looking at me because I don't know what I'm doing. Where is this wretched problem? Who came up with this? Me, unfortunately. I'd like to be able to blame her, but it would be a fib. Okay, so the question that they give us is x of n equals sine pi by 3n over pi n. Ts equals a quarter, the swine. All right. So how do we so the question, I think I can do the problem if I know what I'm doing, but I think what I have to do is I have to say x of, okay, the picture's going to look like this. So it's only defined, my function's only defined at every fourth value, so I've got 0, lost my pen, it's defined at 0, n is 1 of the old signal corresponds to n is 4 of the new, doesn't it? So it's non-zero at 0 and 4 and minus 4. So x of m equals 0 or sine pi by 3 m over 4 if m is a multiple of 4. That's all over pi m over 4. Is that correct? Do you see what I'm trying to say? If m is the integer labeling the bottom axis here, 0, 1, 2, 3, 4, etc., I think that that's what my function is in terms of the m. Shamila, isn't that true? She's not convinced. I'm not saying I'm right, I'm just discussing it with you guys, okay? You're all qualified people. I'm just trying to interpret how I would use that signal. And so if I'm saying every fourth beat of the new sampling, I coincide with the old one. So if n was 1 in the old sampling, I think m is 4 in the new sampling. But I have to take a quarter of the m value to find the n value, don't I? Is that right? I'm sampling 4 times as fast. So I think my x of m would be this. So let's insert a new page. So what I would claim to you is that x of, let's call it x of n, but just to understand it's the new n, is sine pi n over 12, and I'll put a 4 here, all over pi n. That's my x of n, except that it's only non-zero on the 4th beat. So it's that multiplied, not the convolution symbol, multiplied by some d of n, and my d of n is this. 1, 0, 1, 2, 3, 4, 1, and at minus 4 it's 1, and it's zeros everywhere else. It's the product of those things. If that is truly what they want me to do, Jay, do you understand why I'm saying that? Now, we know how to work out the spectrum of that, I think. We do. If that's the product, we do know. If that's the question, we know how to find its spectrum. Are we recording all this precious stuff? Maybe.
Do we even have to go that far?
If you know a short way around it, Luke, I wouldn't mind hearing it.
So if we had take the original x of n, the sine pi 3n over pi n, and then we take the we just take the ts to be a Sha function of.
Okay, just a second. Speak in English. TS, what do you mean by T? Oh, TS, the sample time.
Yeah, turn that into a Sha function of.
When he says Sha function, he means.
The Dirac comb, the.
He means something that looks like this. There's a Russian letter that looks like, I forget whether it's this one or this one. He's talking about, there's a Russian letter that looks like, I'm going to end up making a rude gesture, but something like that. It's like sort of an upside down M and it's straight lines. So he's saying that this shape here, I guess, is a Sha function.
Yeah, and then we usually just put the Sha and have a subscript be the period. So
I see.
That'd be Sha subscript 4, because that ostensibly would.
You're right. This picture I've drawn down here is what he calls SHA-4 because it's deltas repeating every fourth beat. Okay, go ahead.
So we can just do a Fourier transform of x of n. We can just do a Fourier transform of the Sha function there, which puts out another Sha function.
Absolutely. It's the only quibble I think I have with that, Luke, is that I think that your x of n has a 3 on the bottom instead of a 12. And I do think I need to change, don't I need to change that to a 12? Because I think that they're making me use my sample, if my sample time is a quarter, then I need a bigger number on the bottom.
I thought that was kind of wrapped up in the Sha function.
I don't see how you go. I don't think so. They've redefined time. Now, I think I know what you're thinking about, because when we talked about sampling a continuous time function, we said multiply it by this thing you're calling a Sha function. But and that's what we're doing. This is kind of familiar now. It should be kind of familiar, because what we're doing here. Do you remember we did this we said sampling can be thought of as you multiply x of t by periodic delta functions, right? And what we've got here is this thing here multiplied by periodic delta functions. But I think, Luke, that they've redefined the time. I mean, when we did it with continuous time, our frequency was radians per second. They've defined frequency in radians per sample time. And that's the only thing I would quibble with you about. I think it's clear that because they've made the sample time 4 times smaller, the frequency of our basis function looks 4 times smaller as well. If the sample time's smaller, the frequencies present look smaller, expressed in terms of that frequency. Sam, whatever you're doing, listen to me because I need your help. Okay, so I do think, I think it's clear that they've if m is basically n over 4, no, m is 4n. My m here is 4 times n. I have to make that substitution. I don't see any way around it, and I don't see why you don't agree. Right? I mean, they're sampling, where did I say this? You're sampling 4 times as often, so m equals 4n, yeah. So I called it n, but I've changed variables from. Maybe I should have just left it as m, so I wouldn't be arguing about it. The m, Jata, you're drifting as well. Are you following what I'm doing?
Yes.
Yes, Alex.
M is 4n, and it wouldn't be pi over 12, would it?
What would it be?
It would be 4 pi over 3.
Why?
Because you're just multiplying it in.
Look, if m is 4n, if I want to, then n is m over 4. That's the substitution I've done. It's fine, Alex, but it's like it's the wrong moment to ask that question because I don't know what I'm doing. I really don't know what I'm doing. So if you ask me questions like that, it throws me more than it should because I'm kind of confused what's going on anyway. Okay, so look, what I'm saying to you is fairly simple in a way. They gave us that signal, x of n. They told us that they're going to sample with a sample time of a quarter, so I'm interpreting that as meaning that you've got to resample this signal 4 times as fast. If that's what I'm being told to do, Sarvash, then I've got some choices. I don't know what that means. But if I assume that I've got to enter zeros in between the original sample points, then we get this picture, and the m value, well, n is m over 4, and unless n is an integer, do you agree n is m over 4? The old time is a quarter of, is the new time divided by 4, and only when n is an integer do I have a non-zero value. So x of n, but I'm going to say that what is really going on is x of n is this, but I'm multiplying by Luke's Shah function. Yes, Jake?
So the new function is when you sample it different and then you're multiplying by the function to get the zeros?
This new function here gives the right shape when n happens to be a multiple of 4, but I've got to multiply by this to put the zeros in between, yes. Make sense, Sarvash?
So you're just redefining the function. So
Well, I'm just writing the function in terms of a new integer so that it's 0 in between, and every time my integer hits a multiple of 4, I get the original thing back. Okay, if that's what they want us to do, that if that is indeed what we're supposed to do, we know how to do this, because we already did exactly this when we did, it's essentially the same thing when we did sampling in the first place, because we said we took a continuous time function, multiplied it by periodic delta functions with. Well, in this case, our periodic delta functions, what we have are delta functions that were a delta of n minus 4, I better I didn't call it m, 4p. And we've got a sum over p equals minus infinity to infinity. That's what this thing is. Right? And we know what that's going to do. Luke thinks I'm full of it, but I'm going to stick to my guns for now. So whatever our original, you see, if I'm right that this is the function here, it's basic, that's a sinc function with a W of pi by 12, I think. Okay. I should have better make that a W. So when you take the basic function, you're going to have a rectangle from minus pi by 12 to pi by 12, and when those periodic delta functions have a period of 4. So what are the delta functions in frequency domain going to look like? You remember, Jeremy, I hope, that when we had periodic delta functions in time, when we transformed them, we got periodic delta functions in frequency. Do you remember that? Do you remember what the spacing of the periodic delta functions in frequency is going to be? We're going to get delta functions in frequency. What's their spacing?
Some sort of factor of the original 1 to pi, I think.
It is, yeah. If the original ones are further apart, do these get further apart or closer together? Do you know what I'm talking about by this question? This is good practice of some of our basic ideas. Hua, do you know what's going on here? Well, please ask, okay? Because I don't want to... I'll take it from the top because I don't think there's any harm in that because we've been all quite confused, okay? Jatta, pay attention and make sure you follow this time, okay? What I'm saying is that we were given a question where we had an x of n equal to this in discrete time. Make sure you follow every step, okay? Shout out if I go crazy on you. But they're asking us what would happen if you sampled that with a sample time that was a quarter of the... Now, they don't tell us what they mean by doing that, but... Yeah, okay, that's fine. Which, all right, well, all right. So I'm redefining my integer n to be 4 times as big. So I'm defining an integer m that's 4 times as big. I substitute in terms of the new integer, my function is this, but I have to multiply by this function, which has zeros. Okay. Well, what I'm saying is, if these two functions are multiplied in time domain, their transforms are going to be convoluted with a factor of 1 over 2 pi, Alex. If they're multiplied in time domain, there's a 1 over 2 pi when you go to frequency domain in the convolution. If they're convoluted in time domain, no 2 pi. So I'm saying to you that my deltas in time domain look like this. Delta of n minus 4p, where p is just any old integer. And the sinc function has a width of pi over 12. So what I'm saying to you is, what will the delta functions in frequency domain look like? How far apart will they be? Now this is a simple question about basic Fourier series now, because when we find the transform of what Luke calls the Shah function, we're finding a transform, Sarvash, of a periodic function. So we have a recipe for this. We say periodic function, therefore we find the... Exactly, Fourier series. And when we find a Fourier series, what's the very first thing we find? It's... Back a bit. When we're actually... Even further back. The very first thing we find when we find a Fourier series is we identify the period, is what I'm driving at. I know you know it, it's just I can't ask a question. It's hard to ask the right question. The very first thing I try to get you to do when you're finding a Fourier series is find the period. What do we do with the period? What's the period got to do with the spectrum of the signal? If you know the period of the Fourier series, what can you say about the spectrum? What frequencies are present in a Fourier series? Exactly. So if you know the period, then you know the fundamental, don't you? So what's the period of our deltas? 4. So omega 0, or whatever we're calling it, is... Exactly. Is pi by 2, isn't it? Right? So... our deltas in frequency domain are spaced by what's the spacing of in frequency domain of a periodic? The spacing is omega 0 because the frequency is present. You have e to the j k omega 0 n. K omega 0 is the frequency. It's an integer times the fundamental, isn't it? So what I'm trying to say to you is, if we know that we've got these periodic deltas and the period is 4, which it clearly is, the way we've set this up, then the fundamental is 2 pi over 4, fundamental frequency. So the spectrum is going to have frequencies present at multiples of pi by 2. Right? Why is this all okay?
Yeah, I think it's just like it's kind of for the horizontal line is just like a multiple of omega 0, right?
The frequencies that are present are 0, omega 0, 2 omega 0. This is that sum of deltas, let's call that d of t. Big D of omega is going to look, the transform of that is going to look like this. And so what we're saying, this is 0, pi by 2, 2 pi by 2, 3 pi by 2, etc. Now this omega here, I hope I've been consistent enough. I haven't been consistent about my notation. Sometimes I've used capital, sometimes lowercase. But this omega here is radians per sample time, I hope. I hope I'm being consistent about that. Anyway, what's our overall spectrum going to look like now? What do we have to do to find our spectrum from this is our x of omega, this is our d of omega. We had the two things were multiplied in time domain, so in frequency domain it's convoluted. It's 1 over 2 pi times the convolution. And do you know what the convolution gives?
Just repeating itself.
Yeah, if you convolute a signal with a delta, you get a copy of the original that's displaced to where the delta is. So every single, have I got space here? No. So if I say to you that I have, and there may be all sorts of errors in what I'm doing, but I hope not, if our x of omega, what was the width of x of omega? Pi by 12? It goes from minus pi by 12 to pi by 12, and we convolute that with deltas that are spaced by pi by 2. What we expect is, what do we expect? We expect at 0 something that stretches from minus pi by 12 to pi by 12. Then when we go over to pi by 2, and I'm going to have trouble drawing this, aren't I? We get something that stretches from pi by 2 minus a 12th, so that's it's 5 twelfths, isn't it? 5 pi over 12 to 7 pi over 12, etc. And a mirror image d oohickey over here. So that's what I think this sort of sampling would do. If that's what we're supposed to do, that's what I think the result would be. Does that seem reasonable? Let's try and think about that for a second. I mean, there's two things going on here. Our original if I asked you to justify that answer, Jake, in terms of common sense, could you? I'm not sure I could. I want to try and think about it for a minute. Our original signal its transform would have been a sinc function. We were originally given a sinc, right, Sarvash? It's a sinc. But the thing I want to focus on is in frequency domain, what would that sinc have looked like? It was sine of pi by 3 times n. So our original signal would have had a width plus to minus pi by 3. Now we move into a sampling rate that's 4 times as big. So do we expect our So we're redefining frequency as radians per sample time, and our sample times got smaller. So does our original signal get wider or narrower? Pi by 2 on our plot is actually corresponds, pi by 2 on our frequency plot corresponds to a bigger frequency now, doesn't it? Because the sample time's smaller. Is this right? Am I saying this the right way around? So our original signal that ran from pi by up to pi by 3, I think it's going to look narrower if the frequencies that we're plotting on are bigger. So it makes sense that this doohickey has got narrower under the new sampling, right? Now, what about the spacing of these copies? Because anytime you sample, you expect copies at... But the thing is that there will be copies at pi and minus pi. We've got these extra copies came about because we aren't actually, because we're not sampling we're not sampling the original function every beat. We're sampling it 4 times more slowly in the new setup, right? So it's like we're using this higher frequency, but it's kind of like we only sample every 4th beat. So instead of the copies being at minus pi and pi, the copies are actually happening much more often. They're happening 4 times as often. So I think that might make sense. Why, do you understand what I'm trying to say? It's not all, I mean, it's not all that complicated, except that it's just a bit much to deal with all at once. Okay, so I think that that's my answer to the problem. If you can spot anything, Jata, did you follow that time? If that's what they mean us to do, then I think that's what we're going to get for a spectrum. And I mean, I think we did the math reasonably carefully, so, or at least close enough. Okay, Luke's not looking very happy, but he's not tearing me a new one, so I'm thinking that I just should move on, keep moving. The other, I'll just, let's see. There's another way that you could try and answer that question that might interest you, and I'll just mention it briefly. I've made a little recording about this, so if you're interested, you could look at it. There's a thing called a zero-order hold. Have you ever heard of that? What is it, Sam?
It's like when you just connect the dots, go straight across, can't stuff.
Pretty much, yeah. So in other words, if we had sampled a signal and we got values like this, a zero-order hold is where you create a continuous time function out of your sampled function by basically applying a zero-order hold. Means you draw a straight line. Every time you sample, you just assume that the function stays at that value until the next time. Have you heard of this before? Okay, well, I'll just tell you about it briefly now in case you're interested. Don't worry, I'm not going to go nuts with this. Well, do you understand what I just said? So what you basically do is you define HO to be this. You make that TS be the sample time, you make it be height 1. That's the definition, that picture is the definition of the zero-order hold. So the histogram that we had up there, that histogram can be written as x of n times h0 of t minus n ts. Now see if you understand that. For every value x of n, you basically take this zero-order hold function and you say It's 0 except in a narrow range. When is this h0 not 0? Well, when t gets a little bit bigger than n times ts. So if you're looking at the nth sample, when t is just a little, the nth sample, you want to use the value xn of the nth sample for times that are just a little bit bigger than n times ts. So this will make that happen, won't it? Sarvash, do you understand how that works? So that is like a reconstructed version of your continuous time signal. It's sort of an odd way to do it in a way, but if you take the sampled thing and create a histogram out of it, that's a way of writing it. And this is cute because you can write this as, how do I want to write this? Suppose you write this as h0 of t convoluted with x of n delta of t minus n ts. What would that thing give? The point, I'm going somewhere with this, the point I'm going to try and make is that when you sample a signal, x of t, the sampled signal, xs of t, we write it as, how do I want to write this? Something like x of nts delta of t minus nts. Do you agree that that would be a way of writing the sampled signal? I'm trying to write down the original x of t multiplied by deltas that spike at. Right, so that, or sometimes people write that as x sub delta. It's the original signal multiplied by deltas. Do you agree with that? Sam, do you agree that the sampled signal could be written like that? Well, the point I'm trying to make is what we have. I'm trying to rewrite our function with the zero order hold in terms of this. So this could be written as x of n delta of t minus n ts. What I'm saying to you is if you take this x delta here, if you convolute that, and I really need a sum over n to make all, it not just be a single spike and to include all the spikes. If you convolute this h0 with, for example, delta of t minus nts, what do you get? I'm bringing this up as practice of knowing how deltas work. I'm hoping it would just interest you a tiny bit. Do you understand what the heck this thing is? Right, this thing is a sampled signal. Right? Poir, is that okay? So now imagine convoluting h0 with the delta that appears in that sum. What would you get? That's exactly right. Did you hear what he said? If you convolute anything with a delta, you get a copy of that thing at the place where the delta spikes. So if I convolute h0 of t with this delta, what I'm going to get is h0 of t minus n ts. See how that works? Well, the point is that this is what appeared in when we introduced the zero order hold. We had, wherever it's gone, this is our set of histograms. So what this all shows is that the difference between the set of histograms was sum over n of x of n h0 of t minus n ts. Sarvash and Jake, you getting that? Well, that can be written as h convoluted with sum over n of x of n delta of t minus n ts. Right? And my only point to you, Sam, or Luke, is that if you want to understand what the zero... See, one way of trying to do this problem that I thought is maybe we could think of it as use a zero-order hold. If I don't know the values in between, assume they're equal to the old values. And that would be equivalent, Jake, to using a zero-order hold. Well, so this histogram with the zero-order hold, it's equivalent to taking the zero-order hold and convoluting it with the sampled function. So one way to do this problem would be to say, take the spectrum of the original. This is a different interpretation of the question. The way we just did it a minute ago was to insert zeros. What I'm doing here is inserting ones, basically, aren't I? If you do this, you could take the original function that's sampled, the original sampled function, and convolute it with this h. And h is a rectangle, so its transform is going to be a sinc function. It's going to be a wavy thing. So you're going to convolute a wavy thing in frequency domain with your original spectrum, and you'll get an even wavy. You'll get something that's a bit of a mess.
So both of these are imperfect, but what you're saying is a zero-order hold is probably more likely that's what's happening with your data than zeros.
Seems that way to me, but I mean, the thing that's clearly the question is not expecting this amount of agonizing and messing around, is it? So I'm not answering the question, but I think it's interesting to talk about. That's all. Now, there's a picture somewhere in here of the effects of the zero-order hold, and I'll pass it around so you can have a look at it. Except their index isn't that good. Just a moment. I will find it sometime before the end of today. Maybe. It's in here somewhere, I know. Here we are. So, what they do here is they say if you have a signal x of omega, and you can't see from where you're sitting, but if this is the x of omega, if you sample it, you get something with lots of copies. If you apply a zero-order hold, then they sketch the zero hold here, and then the bottom picture is the spectrum, the sampled spectrum convoluted with the zero-order hold. So if anybody wants to look at that, I'll pass it around. So, but I just wanted to illustrate how you can use the math that we've been fooling around with to analyze whatever comes up, okay? So I thought that was kind of a cute little thing. Did you understand? You understood that? Well done. At some point, I suppose if I gave you enough warning, I could say explain how a zero-order hold affects the spectrum of a sampled signal. I mean, that would be an interesting question in a way. Okay, so I spent some time trying to figure out the answer to that question. I still think I'm probably not doing it right, but I think introducing the zeros may have been what they expected. But I didn't find any hint of that actually in the text that I'm using, so I'm a bit confused. All right. So, I strongly suggest you look at this list before tomorrow in case you'd like to ask some questions about it. Yes, Sarvash.
Will we do number 5?
we can certainly try. Which one is figure 3? All right, we can try. Well done for just diving in and picking one. So, okay, let's try and do this. I don't know what this involves, so there'll be a lot of humming and hawing here. So it says use figure 3. So figure 3 looks like this. Hoo boy, what a mess. I think, is that the right figure, Shamila? Is that the right figure? Savash, is that what you were expecting me to draw?
Yeah, I think so.
Is this number 5?
It might be.
System depicted in figure 3.
Yeah, this is the
Okay, because so you've drawn it on the back.
Oh, yeah.
So this is the figure. All right. Z of t, where's Z? Oh, I'm sorry, I failed to mark on Z of t is the signal here. Okay, so it says sketch Z of omega and Y of omega for the following cases. All right, I have no idea what I'm doing. They want us to put in W of... Have they told us what H of t is?
I think it should be.
Oh, okay, yes, they do give us an H of t. They tell us, first of all, W of t is cos 5 pi t. H of t is sine 6 pi t over pi t. Is that all I need to know? Oh, and they... What? There's something not quite right here, because on this sketch you've got x of n omega sketched, and then you've got this sketch that says W of t, but they give us a different W of t.
Yeah, this refers to only C5.
Oh, all right. But the x is always x.
Yes.
Sorry, Shamila. Okay. So, and we're given x of omega looks like that. It's got height 1. It goes from minus pi to pi. All right. I may have enough information to do part 1 now. Okay, so make a note of that, because very soon the whole problem specification is going to move off the part of the screen that you can see. So, they've given us a spectrum going in. They've given us a W of t and an H of t, and we've got to sketch the spectrum of Z of omega and Y of omega. Is that right? Yes. Okay. We can probably do that. Oh, you're just passing it round. I thought, what's the matter? I don't know if that was interesting, Sam. Hopefully a teeny bit. Okay, any thoughts? Do you understand what the question is saying? Though it's indicating that we've got some multipliers there, right? Those boxes, the circles with the x's are multipliers, aren't they? So you're going to take x of t and multiply it by W of t. So based on our advanced training in this subject, I think we can fairly rapidly do some of these pieces. Everybody just stare at it for a minute and see if you can see what's going to happen. I think it looks like so many problems, it looks an awful lot worse than it is, this first one. Jeremy, do you know what's going to happen?
Looks like it's just to multiply WT and XT.
Right. That's right, to get Z of t, but we probably want to, they're asking us primarily to work in frequency domain. Yes, Sarvash, what's up?
So since we're multiplying them, we can convolve them in frequency.
I think we better, yes.
And since the cosine will just be a pair of delta functions. We'll just
Oh, that's right, it's a cosine, isn't it? I was thinking it was... Because we've got a sinc function over here, haven't we? I thought we had all sinc functions. Right, W of t is a cosine. Yeah, so all right, so first of all we've got to work out what W of omega is. I think. And he's right, you can just look up W of omega in a table, it's a pair of delta functions. Does everybody agree with that? So W of omega should be, where are the delta functions? I don't know about factors of 2 pi, but if we probably need, they're probably of height pi. Not sure about that, because and they're at minus 5 pi and 5 pi, I imagine, aren't they?
why are they like pi?
Well, I'm not sure about this part, but if you transform e to the j omega t, don't you get 2 pi delta of... If you've got e to the j omega 0 t, isn't the transform 2 pi times delta of omega minus omega 0? So I was just trying to put that factor of 2 pi in. I'm not... If you've got the table, you could get it right, but I was thinking that's what we would get. Is that correct? So that will be our W of omega. This is a nice little question because it's important, when you come out of this course, if you were brave enough to go on to the next signal processing course, you're supposed to know what happens to a spectrum. Multiplying a signal by cos of omega t is a very basic operation. Why do you multiply signals by cos omega t? When you transmit a radio signal, what do you do?
Multiply a carrier wave by the signal.
Right. Right, so you're always multiplying some x of t, which has like speech frequencies in it, by cos omega 0 t, where omega 0 is like a radio frequency. That's what modulation is. Do you know what modulation is? Right, you take a signal that's in the speech range and multiply it by something much higher frequency, because you're going to transmit the whole mess by radio. So it's tremendous, multiplying a signal by cos omega t is something that we really ought to know all about, right? And that's what's happening here. Maybe this is an amplifier of some sort. I don't know. Maybe this is a very simple model of some stage in a radio, right, Jetta? Do you understand? Okay, so if we multiply our original x of t by a w of t, we're going to convolute this x of omega with this. I think that's what Sarvash said. So what will we get? See, one of the things that I try and stress is that convoluting with delta functions gives copies, and the copies are located where the delta functions were. The centers of the copies are at the places where the delta functions were. Well, we know that, don't we? So our sketch of, what was it called, z of omega? Our z of omega is going to look like x of omega. Let's try and get rid of this line. but it's going to be, if I was right about the minus 5 pi and 5 pi, we've got these things that are of width. This is going to be minus 6 pi, this is going to be minus 4 pi. Similarly, 4 pi to 6 pi, not a very good sketch, but I'm in a hurry. I think that's the z of omega for this one, isn't it? Z of, yeah. Do you agree that's what z of omega should be expected to look like?
And make sure that the height is pi.
Oh, picky. All right. I think that's right, isn't it? Okay, so that's that one. Is Sharmila making little noises of concern or not, or what? What's the matter? Did I do it wrong? Is she even talking to me?
Yeah.
What are you worried
If
about?
convoluting, we would get 1 over 2 pi term in frequency domain.
Ah, that's what she's worried about. Okay, yes. Multiplied in time domain, 1 over 2 pi times the convolution in frequency domain, right? So the height isn't pi, it's a half. Do we all agree about that? Do you know what I'm talking about? Multiply in time domain, convolute in frequency. Convolute in time, 1 over 2. There's a 1 over 2 pi in that relationship. There's only a 1 over 2 pi in that because of the way we define the Fourier transforms. There's always these 2 pi's floating around, but the way we define things, yeah. So that's not height pi, it's height a half. Thank you. Since we're recording this, it's going to be embarrassing if I have factors of pi wrong, but not terribly because I don't really claim to be getting the factors of 2 pi right necessarily. Okay, that's all good. So that's what we're putting into this. I don't know what it is, maybe a radio something or other. Now, our h of t is sine 6 pi t over pi t. And we're going to fire this z into that box. So what's going to happen? I think our intuition should be pretty good for working out what that box does to our signal now. What does that h of t look like? Well, Alex, do you know what's going to happen now?
H of t is a square wave.
Well, yeah, careful how you say it. H of t is sine 6 pi t over pi t, right? Is that a square wave?
It's the same function.
Yeah. I'm sorry. I'm sorry. I've got to cross the i's and dot the t's. You know. That's as funny as I get. Nobody's even paying attention to me. So it's a sinc function. So in frequency domain, it's a square wave, is what you're telling me, right? What's it? Boy, the degree of engagement in this class is just astronomical. I'd say it was like drawing teeth, but there'd be far more reaction if I was drawing teeth, wouldn't there?
Well, it's not a square wave because it's not periodic. It's just a.
It's not periodic. No, it's
filter.
okay. It's a rectangle. It's a low-pass filter, sure. So the h of in the problem we're doing currently, h of omega is this. It's a rectangle. I guess it's of height 1, and it's from where to where?
Negative 6 pi to pi.
Thank you. Minus 6 pi to 6 pi. So what does that do to our x? So we put that. What's the matter? Is that wrong, Sam? What are you shaking? You're just shaking your head for the heck of it. I don't think it does, actually, does it? That's what this was. This was a soft pitch. This was a, what do you call one of those? They're given as a baby one to begin with, which I'm always grateful for. I mean, we want a nice structure. Makes it easier to do it if we know that it's going to start easy and get harder. So it doesn't look like that does anything at all to our signal because our z of omega wasn't it all between minus 6 and plus 6, so it doesn't do anything. Your z of t is convoluted with h of t, but that means we multiply in frequency domain, and you multiply this with your original, and I don't know what it's even called, but the thing that comes out of the h of t is just equal to z of omega. Okay, now what are we going to do? Well, according to the picture I've got here, we're going to multiply by another cos 5 pi t for some unknown reason. Right? So we've already established that cos of 5 pi t in frequency domain, we know that that is, we've got minus 5 pi plus 5 pi, and we decided those were both of height pi. Right? So we've got to convolute our z of omega with that. True? Now z of omega, thank you for nodding at me, Jake, it really helps. Our z of omega looked like this, and they were of height a half, centered on minus 5 pi and plus 5 pi. So when we convolute those two things, what will y of omega look like?
You get one of those at minus 10 pi and one at plus 10 pi, and then some nonsense in the middle where they're convoluting each other again at the origin.
What was the last thing you said? I mean, that's all correct, I guess, but I couldn't understand what you said at the end about what's happening in the middle.
I said some nonsense.
Some nonsense. All right, yes, there's definitely some nonsense. If you convolute these two deltas with these two thingies here, you get a copy. Let's see, there's going to be a 1 over 2 pi before we do anything. So everything's of height. So I think what I'm going to have is stuff at minus 10 pi, 0 and 10 pi, right? I think I'm going to have one of these doohickeys of height a quarter over here, another one of height a quarter over here, and there's going to be two of them hitting in the middle, so I think it's going to be height a half in the middle. Does that seem reasonable? Jake, you're not sure? Felipe? How are you doing? Haven't seen you in a while, you blighter. Oh yeah, did you know that you were a blighter? Blighter. It's you, you're a blighter. It's Felipe. A blighter. Snoopy, when he was... Do you know who Snoopy is? He was always flying his Sopwith camel. The poor blighters down there, blighters are... I don't know. You're a blighter for not coming to class. It's a very, very mildly derogatory word. And you're a blighter because you only come to class once in a while. It is. It's affectionate, let's put it that way, okay? It's a friendly remark. I'm trying to tease you a teeny bit. You're a... You do. You absolutely do. It's a bit positive considering what your class attendance has been like. Just kidding. Blighter, do you know what this is? Felipe, do you agree with that answer? There's a little non-committal there, but I'm just going to keep going. Alex, how are you? I think that's right for the first part. The next one, I'm not sure we have time to do it. The next part, part B, the only change that I see is they change the h of t so that instead of sine 6 pi, it's sine 5 pi. Right? So that's pretty easy. If the h of t, instead of having a 6 pi in it, had a 5 pi in it, what's going to happen?
The absence are going to get locked off.
What were you going to say?
Some of it's going to get filtered out.
Exactly, as you both said. If this is changed from 6 pi to 5 pi, then where's z? Z is on the way into, z is still the same, but what comes out of the h of t is going, so it's not called z, it's, let's call it z out. What comes out is going to be that. And so when we convolute with the cosine again, we're going to get copies of this. Now let's see if I'm right what that's going to look like. I think that's going to look like this, and this, and a small, stab it. And that's going to be, I think that's what we're going to get. Is that right? Or no, I think that's right. Is that correct? Yeah. I mean, it's for all I know, this could be back to front, but I think that's right. Does that seem okay? So that's part B. All right, well, I don't think we have time to, has everybody written down anything they're going to? Let's just state what the last part is. The next thing they give us is the W of t, which is the very first thing you multiply your signal by. They tell us WT is going to be a series of squares. There isn't a scale. Sharmila, there must be a scale on this thing. Can you find it? I guess you're going to have to grab that. The W of t becomes this. Do you know what the scale is on this sketch, please? There's got to be some. W of t is this, and h of t equals sine 2 pi t over pi.
5.
Where? It's height 5. What's the horizontal scale?
Oh, 0,
1, 2. So, okay, 0, 1, 2. All right, so, thank you. So that's our h, that's our W t of t and our h of t. So, we're going to multiply our signal by this W and then pass it through this h of t. So let's think about that for a second before we stop. And I don't know if we need to do more than just think about it, or you can tell me tomorrow if you want to do more of this, or whether we've thought about it enough. So we're multiplying our x of omega by that W. So how are we going to figure out? They want us to find z of omega, which is the transform of x of omega, x of t times w of t is z, and they want the transform of that. So we're going to say it's x of omega convoluted with w, and I do need a 1 over 2 pi there, don't I? So what can we say about the Fourier? We know x of omega, we know it's our little rectangle that we started with. So we need to know what the spectrum of that w is. Tell me what you think the spectrum of w is going to look like. What's the, right? That's what we're trying to understand here. This is a good question. It's all good practice. What's the spectrum of W going to look like? Savash, you're my man for this. I always go to you on this. What do you know? If you're trying to find the spectrum of that W of t, what do you notice immediately about it? It's periodic. There's the word, isn't it? It's that word again. It is periodic, right, Hua? So we're going to find a Fourier series, and the very first thing we find when we do our Fourier series is the period. And the period in this case is I think it is, isn't it? Isn't it 2? Is it 2? Find the period's always the hardest thing for me. Is it 2, Luke?
Looks like 2.
Sure does, doesn't it? So if the period is 2, omega 0 is 2 pi over the period, so it's pi. So the point is, we're going to have to, we're going to get, the spectrum is going to be delta functions in multiples of omega 0. So we're going to get copies of our original signal, and the point is going to be how many of them are going to make it through the h of t, etc., etc. So have a think about that, and maybe we'll do some more